Have you ever wondered why even the most sophisticated machine learning models can never achieve perfect accuracy, regardless of how much you optimize them? It turns out some errors are simply baked into the data itself, creating a fundamental limit on performance. In machine learning, specifically within the Bias-Variance Decomposition framework, the irreducible error is the portion of a model's prediction error that cannot be reduced by any learning algorithm. This error represents the inherent noise or randomness in the data-generating process itself, making it impossible to eliminate. This error exists because the relationship between the input features and the target variable is rarely perfectly deterministic in the real world. Imagine trying to predict tomorrow's stock price. Even with perfect knowledge of all factors, unforeseen events and random fluctuations will always introduce some unpredictability. This intrinsic variability, or noise, means that even a theoretically optimal model that completely understands the underlying function would still make mistakes when predicting future outcomes based on noisy data. Understanding the irreducible error helps us set realistic expectations for our models. While we cannot eliminate it, we can acknowledge its presence and focus our efforts on minimizing the reducible errors, which are bias and variance. This means building models that are complex enough to capture the underlying patterns without being overly sensitive to the noise in the training data, which could lead to overfitting. This theoretical minimum error is sometimes referred to as the Bayes error rate, representing the lowest possible prediction error achievable for a given dataset. It acts as a benchmark, telling us the best possible performance we could ever hope for, even if we had an ideal model and infinite data. Recognizing this helps us avoid endlessly tweaking a model in pursuit of an unattainable zero error. Ultimately, recognizing the irreducible error empowers us to become more effective machine learning practitioners. It guides us to strategically invest our time and resources into addressing the types of errors we can actually control, helping us build robust and reliable models while understanding their inherent limitations.